Hello. So in the last 3 lectures we have seen this notion of duality. In the next 2 lectures we will try to see some kind of a geometric interpretation to duality. This part is taken from Professor Sundar's notes. So before we go into it, here are some basic facts that we should be aware of. So consider this picture first. Okay. Now I am drawing the half space 2x1 plus x2 less than or equal to 6. So in order to do that, we first drew this hyperplane 2x1 plus x2 equal to 6. And the half space is given by this side. Okay, fine. Now look at this point 2, 1. So coming from the coefficients of this hyperplane. So this is 2, 1. And this is the vector 2, 1. I mean the direction 2, 1. Now notice that this vector is a normal to this hyperplane. See, this just says that the value of 2x1 plus x2 is 6. Now as you keep moving like this, the value of 2x1 plus x2 will increase. So this vector is an outward normal. When we say outward, it's away from the half space. So remember this. If you are given a half space of this form, the vector formed by the coefficients will be an outward normal to the hyperplane defining this half space. Okay. Now let's go ahead. Now one more fact. Okay. Start with these 2 points. 1, 2, 3, 1. Now these two are the vectors, as in the lines joining the origin to these points, and this is the direction given by the vector 1, 2 and 3, 1. Now if we look at all non-negative combinations of them, they will lie in this area. Okay, so for example, if you look at 4, 3, 4, 3 is just 3, 1 plus 1, 2. But on the other hand, if you look at 1, 4, you need to go ahead in 1, 2 and then take a negative of this vector to reach this. You have to go like this and come here. Okay, so remember this fact as well. If we are given n vectors, here we have been working on 2 dimensions for visualizing. Suppose you are given n vectors, the non-negative combinations of these n vectors are points in the cone generated by the lines joining the origin to these vectors. We cannot visualize this in n dimensions. In 2D, this is how it looks like. Okay. So, and in n dimensions, these non-negative combinations are called the cone. I mean the space generated by the non-negative combinations will be called the cone. Now, let's come to our LP. Now, for this and the next lecture, we assume that we have this LP where X is unrestricted. So, we want to maximize C transpose X subject to AX less than or equal to B and no other constraint. We will also assume that the LP is non-degenerate. If you remember, an LP of this form will be degenerate if there are more than n hyperplanes passing through a single point. Okay, so let's assume that is not happening, and let's also assume that there is an optimum. Okay, now let me recall this notion of an extreme point. So an extreme point is a feasible solution of this LP that is obtained as an intersection of n linearly independent hyperplanes from the set of hyperplanes a1x equal to b1, a2x equal to b2, amx equal to bm. Okay, so we can write it succinctly like this. So let a prime denote the set of hyperplanes that define this extreme point. Then this point satisfies a prime x equal to b prime, and for the others it satisfies a strict inequality, a double prime x less than b double prime. Okay, since we are assuming non-degenerate, it will be a strict inequality. Okay, so we have recalled this notion of an extreme point. Now what we are going to show today is this. Let me read this out first. An extreme point defined by a prime is an optimum if and only if the cost vector c can be written as a non-negative combination of a1 prime, a2 prime till an prime. We will visualize this better soon, but remember that when an LP has an optimum, the optimum occurs at an extreme point. Okay, now what this theorem says is that you look at all these extreme points. Now for each extreme point there will be an a prime, and along with this a prime we will have n vectors. These are the row vectors of a prime. In essence, these are the hyperplanes defining the extreme point. Now the cost can be written as a linear combination of these n vectors. Since they are linearly independent, we should be able to write C as a combination of these n vectors. But this theorem says that if you are able to write the cost as a non-negative combination of these vectors, then that point will be an optimum, and vice versa. Okay, let's picturize this in 2 dimensions. Okay, so this is a picture. I'll guide you through it. For a start, so assume this is x1 and x2. So first look at the orange lines. This one, this one, this one, this one, and this one. So they are the defining hyperplanes. Let me number them. 1, this is 1, then say 2, then 3, then let's take this to be 4, and then finally this one 5. So there are 5 hyperplanes and corresponding half spaces, giving us this feasible region dashed with orange lines. Okay, now these green points are the extreme points. Okay, now we need a cost. Let me assume that the cost is increasing along this direction. This is the cost vector. Okay, so in any normal to this, the cost will be constant and it will be increasing as we move to the right, and hence this is the extreme point which visits it. I mean, when you keep moving these lines to the right, the last extreme point that is visited is this one. So this is the optimum. Okay, now let's try to illustrate the theorem in this picture. Okay, so for that, what I have done here is that at each extreme point I am drawing the normals to the 2 hyperplanes that define the point. So this is in 2 dimension. To get an extreme point you need 2 hyperplanes. So here this is defined by hyperplanes 3 and 4. So this thing is a normal to 4 and this thing is a normal to 3. Okay, these are the 2 red lines. Now what is this vector? This is just the cost vector. So I am drawing all of them at this point. This is the cost, this is the normal direction to this is the normal direction to this. Now you see that this thing is not in the cone generated by these 2 vectors. So this is not obtained as a non-negative combination of these two. Now look at this extreme point. This is obtained as the intersection of the planes 4 and 5. This is normal to 4 and this is normal to 5, and this is the cost vector. Once again, the cost vector is not a non-negative combination. But on the other hand, look at this. This is obtained as the intersection of this one, which is 5, and this one, which is 1. This is the normal to 5. This is the normal to 1, and this is the cost vector. And you see that the cost vector lies in the cone generated by these two, and hence it will be a non-negative combination of these two normals. By the way, recall that this normal is nothing but the vector corresponding to the coefficients of the defining hyperplane. Okay, now you can also verify here and here the cost is not a non-negative combination of the normals. Okay, so this is an interesting characterization. The extreme, I'm recalling the theorem once again. The extreme point defined by a prime and a double prime less than b double prime is an optimum if and only if the cost c can be written as a non-negative combination of the defining hyperplanes, of the normals. So these are the normals to the defining hyperplanes. Okay, so the task for us is to prove this formally. And now the key observation that helps in this is the following. At the optimum extreme point, cost decreases along all directions to the neighboring extreme points. Let me try to explain this. You look at this point. This was our optimum. So what are the neighboring extreme points to this? This one and this one. Now if you move along this direction, you reach this neighbor. If you move along this direction, you reach this neighbor. Now at the optimum, at this extreme point, if you move along this, the cost is decreasing. If you move along this, the cost is again decreasing. On the other hand, you look at this extreme point, which is not an optimum. What are its neighboring directions? This one and this one. Okay, and if I move along this direction, the cost is increasing. Okay, similarly here, if I move along this direction, cost increases. Here if I move along this, cost increases, and here if I move along this neighbor, cost increases. The only place where all the neighbors, in all the neighboring directions, the cost decreases is here. So one more thing to note about these directions. See, if I look at this, so this extreme point has these two hyperplanes. This extreme point has these two hyperplanes. So when I move along this, I am still along this hyperplane. This one I am on it, whereas I am no longer on this. So I go farther from this, and then I reach this. In sense, when I go farther from this, I am also going closer to this, and then at some point I reach this. Okay, so this is the idea. This is defined by, in general, this is defined by n hyperplanes. To go to the neighbor, we have to keep n minus 1 of them intact and go ahead from one hyperplane until we hit equality in some other hyperplane. Okay, so let's try to do this more precisely in n dimensions. So this is going to be our task. We want to characterize this notion of neighboring directions from an extreme point. So from an extreme point, what are the directions to its neighboring extreme points? Okay, so So let's take u0 to be an extreme point, and it's defined by a prime x equal to b prime. There are n hyperplanes here, and a double prime x strictly less than b double prime. Okay, now what I'm saying here is that suppose ui is a point where n minus 1 hyperplanes are intact except the ith one. So there is 1, 2, 3 till n hyperplanes are there here. Assume that you are relaxing the equality from the ith hyperplane. You are saying that a prime I ui is strictly less than bi, whereas for the other n minus 1 you are still satisfying it tightly. Okay, suppose ui is some point. So here is an example. So u1 will be the point where a prime 1 u1 will be strictly less than b1, and the rest of them are all still equality. A prime 2, there will be equality here and strictly less than here, and so on. Okay. Now, the farther this gap is, the farther you are moving away from the hyperplane a prime 1 u1 equal to b1. I mean, like in this picture, if this was the hyperplane, here you are satisfying it tightly, and now as you move like this, you are strictly less than the corresponding coordinate bi, and the farther you move along this line, the more this gap would be. Okay. Now, from each extreme point, there are n rays moving out to its neighbors. You can visualize it like that. Okay. Obtained by relaxing one of the hyperplanes corresponding to the n of them. Okay. And the vectors u1 minus u0. So we picked some u1 which satisfied this, and we look at u1 minus u0. That will be the line corresponding to one of the directions. u2 minus u0 will be yet another line, and un minus u0 will be the nth line. Okay. Now, what is a prime of u1 minus u0? I mean, note that a prime is a1 prime, a2 prime till an prime. So there are n planes, and now I am multiplying that with u1 minus u0. So I will get the first row of a prime multiplied by u1 minus u0, second row of a prime, nth row of a prime, right? Now what do we know? We know that a2 prime of u2 and a2 prime of u0 are the same. They are both equal to b2. So at all these coordinates I get 0, and here it will be some negative value. Negative why? Because a1 prime of u0 equals b1, and this one is strictly less than b1. Okay. Now we can assume that you pick the point u1 such that a1 prime of u1 minus u0 is minus 1. Instead of taking an arbitrary value, let's assume that this is true. Okay. So you can do the same for each ui. Okay. So we have taken n points u1 to u0 such that ai prime of ui minus u0 is minus 1, and a j prime of ui minus u0 will be 0. So if I look at a prime of if I look at a prime of a prime of ui minus u0, it will be 0, 0, 0 and minus 1 at the ith place, at the ith coordinate. Okay, fine. So we have these n rays. So what do we do with them? So here they are. Let's arrange them like this. There are n vectors. Now note that from the previous thing we have, if I multiply this matrix by A prime, okay, so the first column, first row of A prime multiplied by the first column of this will give -1, and the second column, second row and first column will give 0 and so on. Essentially, look at this. A prime of ui minus u0 is this thing. So A prime of u1 minus u0 will be this thing, A prime of u2 minus u0 will be this thing, and so on. So we get this. So what does this show? This shows that u is the negation of A prime inverse. So note that A prime is has full rank and there is an inverse. Now if I multiply by its inverse, we get A prime inverse multiplied by this. Okay, so and this is just the negation of A prime inverse. So the n directions that we wanted are given by the columns of A prime inverse, negation of A prime inverse. So that is what this is. So the directions to neighbors from an extreme point defined by A prime x equal to B prime are given by the columns of the negation of the inverse of A prime. Okay, so just remember this. Now recall our ultimate goal is to show that at optimum cost decreases along each of these directions, and hence from that we should be able to show that the cost is a non-negative linear combination of the outward normals. Okay, this was our final goal. For the moment we have just characterized the directions from an extreme point. Okay, now at optimum, see, why is it the optimum? Because C transpose of u0 is bigger than every other feasible point, right? So C transpose of ui will be less than or equal to C transpose of u0. So C transpose of ui minus u0 will be less than or equal to 0. Now, but this is nothing but the ith column of minus A prime inverse. So C transpose of minus A prime inverse, the ith column of that is at most 0. Hence, we get this result, C transpose of A prime inverse. So I take C and the ith column of A prime inverse, and the dot product of them will be non-negative. Okay, so we get this. So we just have one more step remaining. Let us now try to write the cost vector as a linear combination of rows of A prime. This is what we wanted, right? So here are the rows corresponding to, and then they give vectors a1 prime till an prime. These are the coefficients. Now these are the outward normals to each hyperplane. Now since they are linearly independent, cost C can be written as a linear combination of them. So here, so I am writing C as a column vector. So let's also assume that a1 prime is a column vector, a2 prime is a column vector, and so on. Okay, so and since they are linearly independent, I can write it as alpha 1 something, alpha 1 a1 prime plus alpha 2 a2 prime, and so on. The goal is to show that alpha 1, alpha 2, alpha n, all of them are bigger than or equal to 0. Okay, for the particular case when this comes from the optimum. Okay, now let me just rewrite it as row vectors. C transpose is just alpha 1 times a1 prime transpose, a2 prime plus alpha 2 times a2 prime transpose, and so on. Now I want to show that alpha 1 is bigger than or equal to 0. So here is where we will try to use the inverse. how do I get alpha 1? So look at this. So here is where we will use the inverse. Now if I have A prime and A prime inverse, I get this identity, right? So this says that if I multiply with the first row of A prime, which is actually this thing, and the first column of A prime inverse, I will get this. I'll get 1. If I multiply the second row of A prime and the first column of A prime inverse, I should get 0. Similarly, if I multiply the ith row of A prime and the first column of A prime inverse, I should get 0 when I is not 1. So that is what I am doing. So let me first multiply this thing with the first column of A prime inverse. That is this thing. So this one into the first column should give me 1. So hence I have alpha 1. This one with the first column should give me 0. This one with the first column A1 prime should give me 0. So to get alpha 1, all that we need to do is to multiply C transpose with the first column of A prime inverse. Similarly, to get alpha n, we need to multiply C transpose with the nth column of A prime inverse. So now it just remains to use star. This is what we have shown, that C transpose multiplied by the ith column of A prime inverse is non-negative. And hence we get alpha 1, alpha 2, alpha n to be bigger than or equal to 0. Thereby showing that the cost at the optimum, cost can be written as a non-negative linear combination of the outward normals, which are these things, of the n hyperplanes defining the extreme point. Okay, this finishes the proof. In the next lecture, we will give an interpretation of duality based on this picture.